Well, hello students. Hello seekers of truths. This is mostly for the seekers of truths. Let us look at an example here where we're just kind of playing around with some areas, and this will of course lead to some greater results. But for now, let's look at some of these areas and as a form of review and as a building block to some of the bigger ideas in limit and of calculus. So I have a circle here with a radius of 1, right? And I have an angle here, we call it theta. And I have basically three shapes, a triangle ADC, that's this kind of bluish thing, a sector, which is this slice of the pie here, and then the bigger triangle AEC, okay, the right triangle there. And we want to find the area of all of these things in terms of theta. So let's start with ADC, which is probably the simplest of the areas here for us to find. Let's try to color code this as well. So the area of ADC is equal to 1/2 the base times the height. But the base here also happens to be 1 because that's the radius of the circle. So 1/2 times 1 times the height of this triangle. So this length right here. Okay? So we'll call this H for the height. Now if you see here that this height here is a side length of another smaller right triangle, this one here. So we can say that, I'll write on the side here, sine of theta is equal to h over 1, which is just equal to h. Okay? So h is equal to sine of theta. And that's the height of the blue triangle. So that's 1/2 sine of theta. Okay. The next shape that we should look at perhaps is the shape of the brown, or I would call this purple slice right here. So this is the area of a sector, okay? And the area of a sector divided by the area of the circle, which is pi r squared, is equal to the arc measure of that sector, of arc DC. So in this case, it's just theta over the 360 degrees, or 2 pi radian. We're high-level math learners, so we're going to go with radian instead of degrees. So this question, though, actually simplifies relatively nicely. You see that the pi here cancels out. So I have the area of the sector over the radius squared. Well, the radius is just 1, so this is just 1 squared is equal to theta over 2. So the area of the sector is equal to theta over 2. Okay, so this is my second result here. My first result was that the area of the blue shape there, or the blue triangle. Okay, so let's look at the last one here, which is the area of the big triangle. So this big shape right here, this green shape right here. All right, so I've removed some of the other drawings here just so we can focus a little bit better here. So the area of the other triangle, the area of triangle AEC, is also equal to 1/2 the base, which is 1, times the height, which is EC. Okay, so that's the height, right? But looking at the big triangle, you can see that we could use the tangent ratio. Tangent of theta is equal to EC, which is the height of the triangle, over 1. So that means tangent of theta is equal to EC. Okay? And that, remember, that's the height of the big triangle. So this is also just tangent of theta. So the area of triangle AEC is equal to the tangent of theta over 2. Okay, 1/2 tangent of theta, or we can say tangent of theta over 2. Okay. And there you have it. this concludes these kind of review and warm-up problems, and we will certainly use this result in the next video when we come about a new limit. Okay, so the topic here is limits using geometric properties. Okay, so we're going to see how these three pieces of information get us to a new limit.